So welcome you back to today's lecture. So let us recall what we were doing last time. So last time we introduced the concept of limiting relative efficiency to compare different estimators asymptotically. Asymptotically in the sense that as sample size goes to infinity. And then we realized that in many situations you can compare relative efficiency of two estimators through their asymptotic risks. That means if I can find the expressions for risks of these estimators up to a certain order, then it may be possible to compare such estimators asymptotically in terms of local risk efficiency, limiting risk efficiency. So that leads to problem of finding orders of risks of various estimators. And then what we saw that if you're, so last time what we did is we derived certain expressions for orders of different central movements of x bar. And what we saw was last time we saw a result which says that if expected value of x1 is mu, variance of x1 is sigma square, expected value of x1 minus mu whole cube is mu3, and of course x1, x2 are IID, and expected value of x1 minus mu for whole 4 is same as mu4. So here what I assume is x1, x2 are IID. X bar is 1 upon n summation I is equal to 1 to n xi. If that is the case, then we knew, of course, expected value of x bar is same as mu. Variance of x bar is sigma square by n, which is basically big O 1 by n, so order of 1 by n. Then we also saw that expected value of x bar minus mu whole cube, which is mu3 upon n square, which is order of 1 by n square. And we also saw that expected value of x bar minus mu whole 4, so central movement of sample mean, this is mu4 upon n cube plus thrice n minus 2 upon n square sigma to power 4, which is again big O 1 by n square. And in fact, what we saw is expected value of, in general, if I have to find expected value of x bar minus mu to power 2k minus 1, that is of order 1 by n to power k, as well as expected value of x bar minus mu power 2k is also of order 1 by n to power k. So this gives various orders for the first 4 central movements of x bar. Now many times I may not be directly dealing with x bar, but I may be dealing with some function of x bar. So let us try to see what happens if I replace here x bar by h of x bar. So let me do that result. So let me write down this as a theorem. So suppose x1, x2 are IID. So it is a sequence of IID random variables. Mean is mu. Variance is sigma square. And for some k greater than or equal to 3, derivatives of h as well as h square are bounded. So h is some function. Not kth derivative, for some kth derivative, kth derivatives of h and h square are bounded, that is given to you. and first k movements of x1 exists. Then expected value of h of x bar would be same as h of mu plus sigma square by 2n s double prime mu plus order of 1 by n square, right? And then variance of h of x bar is same as sigma square by n h prime mu whole square plus big O 1 by n square. So this gives you the orders of expressions for the mean and variance of any function of x bar. The idea is just using the Taylor series expansion. So first I use the Taylor series expansion for h of x bar. I am given that first k derivatives of h are bounded. So that means the kth derivative of h is bounded. So what I do is I take my Taylor series expansion around mu of h. So h of x bar is same as, actually what I need over here is I need that the kth derivative of h and h square are bounded in a neighborhood of mu, this mu. So h of x bar is same as h of mu plus x bar mu minus mu h prime mu plus x bar minus mu whole square by factorial 2 h double prime mu. I can keep on going plus x bar minus mu to power k minus 1 by factorial k minus 1, the kth derivative of k minus 1 at point mu plus x bar minus mu to power k by factorial k h kth of xi, and xi is between x bar and mu. Right? That is what the Taylor series expansion says. Now you can call this term as the remainder term. So I try to see what is the order of the remainder term. So let us look at mod of R n is always less than or equal to factorial k and divided by, or what you can do is you can just directly see what is, when you try to see what is expected value of h of x bar is same as h of mu plus expected value of x bar minus mu is 0. So this doesn't go contribute. Then expected value of x bar minus mu whole square is sigma square by n, that is variance of x bar. So sigma square by 2n h double prime mu. Now what would be the third term? Expected value of x bar minus mu whole cube, and x bar minus mu whole cube you have already seen is of order 1 upon n square. So x bar minus mu cube is order of 1 by n square. So the higher orders would be of order of 1 by n square. So I can write down this as order of 1 by n square. Why? Because you can see that Rn is same as expected value of x bar minus mu to power k by factorial k h of k is I, and this quantity is bounded. This would be of higher order of n square, because k is greater, this k would be greater than or equal to 3. So that would be of order of 1 by n square. So that proves expected value of h of x bar is same as So to find the variance of h of x bar, what I need to do is I should try to find out expected value of h square x bar. So I replace here h by h square. So from 1, so let me call this as 1. So using 1 on h square, what do you get? Expected value of h square of x bar is same as h square of mu plus sigma square by 2n h double prime of mu. So h2 double prime of mu. So I need to find out what is the double derivative of h square, and then plus little o n square. So d by d mu of h mu, h square mu is same as 2 times h mu into h prime mu. D square by d mu square of h square mu is nothing but derivative of this. So this is same as 2 times h prime mu whole square plus h mu into h double prime mu. All right. So what I do is I get expected value of h square x bar is h square of mu plus sigma square by 2n, and 2 is over here, so it remains only sigma square by n, h prime of mu square plus h mu, h double prime mu plus big O 1 upon n square. So now using 1 and 2, I can get the variance. So now let us use 1 and 2. So let me call this as 2. So what I do is using 1 and 2, what would be the variance of h of x bar? Expected value of h square x bar minus expected value of h of x bar whole square. Expected value of h square x bar you have already written down over here, which is nothing but h square of mu plus sigma square by n h prime mu whole square plus h mu h double prime mu. Now you have to look at the square of this quantity. So square of this quantity, first I look at the square of each of the terms. So the first term gives h square of mu. Square of this would be order of n square, so that will get consumed into big O 1 upon n square, will I write down? This is O of 1 by n square, so its square would be big O of 1 upon n to power 4, so that also will get, because big O 1 upon n 4 is also big O 1 upon n square. So that will get consumed over here. Then the cross product term will be 2 times this. So yeah, minus plus 2 times that means sigma square by n h mu h double prime mu. plus 2 times this would be little o and big O 1 upon n square. 2 times this would be big O 1 upon n square into 1 by n, big O 1 upon n cube. So everything rest of the things get absorbed into big O 1 by n square. So what happens? You just see this gets cancelled with this quantity. And then h square mu gets cancelled with h square mu. So what you are left with is sigma square by n h prime mu whole square. And that is what you have to prove. Right? So this gives you the orders of expected value of h of x bar and variance of h of x bar for any given function h, provided h has derivatives up to kth derivative h has kth order derivative which is bounded. I would like to emphasize one thing over here. For this, you only need that h has derivative of order k which is bounded. It is only for variance of h of x bar you need h and h square both have a derivative of order k, and both the kth order derivative of h and h square are bounded. Many times what may happen is I don't have h of x bar, but I might have h of Cn of x bar, where Cn is again having a certain order. So let me do that case as well. So as I told you that you can write down a remark that for the expression of expect proof h of x bar, I only need that kth derivative of h is bounded. Whereas for the expression of variance of h x bar, I need that kth derivative of h as well as h square are bounded. Okay, so now let us do the next result, which is as follows. So under assumptions of last theorem, that means your function h has k derivative depending on whether you are dealing with expect proof h of x bar or variance of h of x bar. The k derivative of h is bounded, or k derivative of h as well as h square both are bounded. And you have last theorem. So Cn is suppose a sequence of real numbers. And what kind of a sequence it is? It is of the type Cn is equal to 1 plus a by n plus big O 1 upon n square. So Cn is of this kind. So in a sense, what it says is Cn is going to 1. And your delta n x bar, your estimator is h of Cn x bar. Now if that is the case, then expected value of delta of n of x bar is same as h of mu plus sigma square by 2n h double prime mu, because Cn is of a by n order, so that would also come into the picture. So that is same as plus a mu upon n h prime mu plus big O 1 upon n square. That is expected value of delta of n x bar. And then variance of delta n x bar is same as sigma square by n. So this is same as the earlier one, which is same as variance of h of x bar, sigma square by n h prime mu whole square plus big O 1 upon n square. Let us see the proof. Proof is exactly on the same lines. You have to use the Taylor series expansion. So let me give the proof. So what I do is I define psi of x as h of dx. So psi prime x turns out to be t times h of dx Actually, what you need is it is only in the support of x bar. So let me write down this x belonging to I, where I is the support of x bar. And what would be psi double prime x? T square. This would be h prime t square h double prime of tx x belonging to I. I know, and let me call this as delta n x bar as psi of x bar. So which is same as h of t of x bar. What we have seen is expected value of delta of, so don't write down this for the time being, delta n x bar is how much? Or expected value of h of t of x bar, which is same as expected value of h of t of x bar, which is same as expected value of delta of n x bar, which is same as expected value of psi of x bar. Now, by the last result which we did, this is same as psi of mu plus sigma square by 2n psi double prime mu plus big O 1 upon n square, right? Because last time we have seen what is the expression for expected value of h of x bar for any function h. So h gets replaced by psi, so psi of x bar is psi of mu plus sigma square by 2n psi double prime mu plus little O n square. So what does that mean? But psi of mu is same as h of t mu. Plus sigma square by 2n psi double prime mu. Psi double prime mu is nothing but t square h double prime t mu. Double square h double prime t mu plus big O 1 upon n square. So what I have done is I have at least find out, I put t is equal to Cn, so I get h of Cn x bar. So I put t is equal to h of Cn x bar is same as psi of mu plus sigma square by 2n. Sorry, psi of mu also I write down. Psi of mu is nothing but, so I'm putting t everywhere as Cn. So h of Cn x bar is same as h of Cn mu plus sigma square by 2n Cn square h double prime of Cn mu plus little O 1 upon n square. Right? So that is what the expression for h of Cn x bar is. Now what I need to do is I also further need to expand h of Cn mu. So what I do is I consider alpha t as h of t mu, and let us say t belongs to interval or t belongs to R in fact. In fact, t would be greater than 0 because Cn is 1 plus a by n plus little O n square. So as n goes to infinity, this goes to 1. So alpha t is nothing but, yeah, I expand it around because Cn mu I want in terms of h of mu. So that means I need to expand this in terms of, around t is equal to 1. So h of alpha t is same as alpha 1 plus t minus 1 alpha prime 1 plus t minus 1 whole square by factorial 2 alpha double prime 1 plus t minus 1 to power k minus 1 factorial k minus 1 h double prime h to power k minus 1 sorry alpha k minus 1 1 plus t minus 1 power k by factorial k h sorry alpha k at derivative at point xi, and xi is between 1 and t. So what do you get from here? So alpha t I have put as h of t mu, so that means h of t mu is same as alpha of 1, which is same as h of mu, plus t minus 1 alpha prime 1. Alpha prime is nothing but mu times h prime t mu. So that would be at t is equal to 1 would be mu times h prime. So it would be, yeah, t minus 1 mu times h prime mu, right? Because t minus 1 and alpha prime 1 is nothing but mu times h prime t mu, but at t is equal to 1 it would be mu times h prime mu. This is what it comes to. Plus t minus 1 whole square by factorial 2, and then mu square h double prime mu by the same logic, because alpha double prime t is nothing but t square h double prime t mu, where t is equal to 1 it would be h double prime mu, and then t square at t is equal to mu. So this is what sorry at t is equal to 1 it would be mu square. So this is what it is, plus tn minus 1 to power k minus 1 by factorial k minus 1, t minus 1 to power k minus 1 factorial. Alpha to power k minus 1, again t to power k minus 1 comes, and mu to power k minus 1 t to power k minus 1 h double k minus 1 mu, plus t minus 1 to power k by factorial k mu to power k h k xi. Xi is between because I am experiencing mu and t mu. Sorry, xi is between 1 and t, right? That is what we have seen from there. Xi is between 1 and t. Now I replace just t by Cn. So h of Cn mu is nothing but h of mu. Let me just use some space over here. H of mu plus is same as, sorry, h of Cn mu. So I put t is equal to Cn, so that is same as h of mu plus Cn minus 1 mu h double prime mu plus Cn minus 1 whole square mu square h double prime mu plus higher orders of so on. Finally, it would be Cn minus 1 to power k by factorial k mu to power k h to power k psi. All right? So what do you get from here? This would be same as h of mu. So I'm trying to get what is h of Cn mu order, right? I'm almost. So this is same as h of mu. Now note that my Cn was 1 plus a by n plus O 1 by n square. So Cn minus 1, which is this quantity, would be a by n, and rest of the term would get involved in 1 upon n square. So this is a mu upon n h prime mu plus Cn minus 1 whole square. So Cn minus 1 whole square would be a square by n square. So that is not going to contribute anything. And then higher powers of 1 upon n, so that would be big O 1 upon n square. So h of Cn mu turns out to be this, because I needed what is h of Cn mu and I needed its order. I also needed order of h double prime Cn mu. So what I do is here I just replace h by h double prime. So what do you get? H double prime Cn mu would be h double prime mu plus a mu upon n h triple prime mu plus little o 1 upon n square. So what do you get? So expected value of h of Cn x bar turns out to be h of Cn mu, which is same as h of mu plus a mu by n h prime mu plus sigma square by 2n Cn square, and then h double prime Cn mu is nothing but h double prime mu plus a mu upon n h3 mu plus big O 1 upon n square. Good. Now note that this is same as h mu remains as it is plus a mu upon n h prime mu. Now note that Cn square is 1 plus 2a order of 1 by n. So Cn square, if I have to see over here, let me put it in margins. So Cn square is 1 plus a square upon n square would be big O 1 upon n square. This would be big O 1 upon n 4. So everything gets consumed in big O 1 upon n square plus 2a by n. Cross product of this with n square is n square. This would be n cubed. So the rest is big O 1 upon n square. So when I multiply by this, I only get sigma square by 2n, and rest would be big O 1 upon n square. So only sigma square by 2n would come, and sigma square 2n multiplied by this would give me only h double prime mu. And rest would be big O 1 upon n square. So what I get is expected value of expected value of h of Cn x bar is same as h mu plus a mu upon n h prime mu plus sigma square by 2n h double prime mu plus big L O 1 upon n square. Now what you can do is you can apply the same thing on h square, the way we did in the last theorem. Now if you do that, you get this as h square of mu plus a mu upon n. What is the derivative of h square mu? 2 times h mu h prime mu plus sigma square by 2n, double derivative, so that means derivative of this. Derivative of this with 2 gets cancelled, and you are left with h prime mu whole square plus h mu h double prime mu plus big O 1 upon n square. So now you can get variance of h of Cn x bar, which is expected value of h square of Cn x bar minus expected value of h of Cn x bar whole square. This you have already found. You have to find out the square of this. Square of this would be h square mu plus twice cross product term would come, and that gets cancelled with this. Right? And plus twice this will come, so sigma square by n h double prime mu would come. This with this cross product will be little o n square and so on. So this would be nothing but sigma square by n h double prime mu whole square plus big O 1 upon n square. So this was about variance of h of Cn x bar, expected value of h of Cn x bar. So these expressions are normally useful whenever your estimator is in terms of x bar, because in many situations x bar is a complete sufficient statistic, or at least a minimal sufficient statistic. So all good estimators are functions of x bar. And in many situations, these two results, which give you the orders of various functions of h of x bar, can be useful. So what I'll do is in the next module, I'll do one problem based on that. Now if time permits, in the next module, I'll also show you, last time for example, I showed you expected value of x bar minus mu to power 2k is big O 1 upon n to power k, and expected value of x bar minus mu to power 2k minus 1 is also big O 1 upon n to power k. I'll try to, and then I left for k is equal to 1, 2, 3, I left that as an exercise. So to, if time permits, to have a better insight into what would be the order of expected value of x bar minus mu to power cube and expected value of x bar minus mu to power 4, if time permits, we'll also do that. So that we'll do in the next module. So that's all for this module. Thank you very much.